All right, welcome everybody. We're just going to give a couple minutes to allow people to join. All right, looks like the people joining slowing down a bit, so I think we'll get started. Hi everybody, my name is Julia Potter and I'm the current president of the Women in Mining Arizona chapter. We'd first like to say welcome and thank you for joining us for today's talk about highwall mapping using drone-based hyperspectral imagery at the Ray Mine. It's a mouthful. Before getting started, we just want to give a brief introduction to our organization, Women in Mining Arizona, and why we host these talks. The Women in Mining Arizona chapter, or as you'll hear us say, WIM Arizona, is a nonprofit organization with 5 key objectives, one of which is to educate our members and the public on technology, economic, regulatory, and other mining-related topics. And these monthly dig-in webinars are a part of our efforts to meet that commitment. We'd also like to just give a quick thank you to our 2020-2021 Platinum sponsor, Freeport MacMoran. They make these webinars and all of our programming possible. So thanks so much to them. And then I will introduce Isabel, our speaker for today. Dr. Barton is an assistant professor in the Department of Mining and Geological Engineering at the University of Arizona. Her research focuses on geometallurgy, which combines concepts and techniques from geology, mineralogy, and extractive metallurgy to get metals out of mined rocks more efficiently. Isabel, thanks so much for being here today. I think Megan will now turn the screen over to you.
Okay. Well, thank you very much for inviting me. Let me see if I can convince Zoom and PowerPoint to talk to each other here. All right. Can everybody see my screen, hear me? I can do my best with the interpretive dance if the sound cuts out, but I'm really hoping I'm not going to have to inflict that on y'all. All right, well, thank you everybody, and special thank you to Julia, Megan, Mario, and the rest of WIM-AZ for inviting me to come give this talk. It's going to be about some research that I've been doing with one of my PhD students, Jingping He. And so this presentation really has both of us involved in it, him especially. And in addition, I owe thanks to the cast of thousands who supported it: Chad Williams with the U of A Geotechnical Center, Mark Barton in Geosciences, Sterling Cook and Jeff Cornoyer from Asarco, who helped us set up the study, and then Carson Roberts, Will Rock, and Charlie Kepler with Headwall Photonics, who did most of the hyperspectral scanning and who have been consulting with us on reducing and improving the data. So I may be here giving the talk, but it's really been a very collaborative effort. All right, so I'll start out with a little bit of background on why this study happened in the first place, because I did not, I promise, just wake up one morning and say, why don't I take an incredibly expensive scanner, put it on a drone, and fly it very close to a mine high wall just for fun today. You know, I am crazy, but I'm not that crazy. So I'm going to start out by a little bit of background on how the study came about, and then get into what we did, what we found, and what it means, and hopefully finish in time for some Q&A and lunch. So this map was the study site. Can everybody see my mouse if I move it around? Okay, great. So the Ray Mine is here north of Tucson, slightly south of east of Phoenix. It's a large open pit porphyry copper mine, been operating for some decades. There's a Google Maps air photo and geologic map down there to show you roughly what the mine geology is. Notice, by the way, this is a theme I'm going to be coming back to. There were a lot of blue lines to go with the nice shiny colors on the map. Those are faults. So Ray is a porphyry copper deposit with a very complicated set of faults and structures that cut through it. So it's going to be important later in the talk. So this is what the stratigraphic column looks like in case anybody really wants an eye test. The colors correspond to that last geologic map, but the main important part about this is that the Ray mine has a very complicated geology. It is based fundamentally on laramide porphyry intrusions, but there's also a whole tertiary volcanic section above that. It's sitting on Proterozoic and Paleozoic sedimentary rocks, igneous metamorphic basement, and there are various basalt flows and diabase intrusions further complicating the picture. And so this is geologically as well as structurally an extremely complicated deposit to work in, with a lot of natural variables to sort out whenever we're dealing with map data from this mine. All right, so this is the how this study happened part of the talk. And what I'd like to draw your attention to is this little red blob high up on the Highwall. The map here is a radar image showing acceleration, basically looking at the movement of rocks on the mine Highwalls provided by the Geotechnical Center of Excellence. And so you can see red here means lots and lots of movement, whereas stuff that's in the green zone is pretty well stationary. And high wall movement is a problem because obviously the high wall is supposed to stay where it is and not start sliding into the pit or doing other forms of monkey business that could make us have a very bad day indeed at the mine. Now, Ray is, most mines have radar systems precisely because they're used to a certain amount of high wall activity. And normally at Ray, it's connected to some of those structures, the faults. Whereas the moving red blob of interest up here was bounded on the top by faults, but there was no particularly obvious reason why it should have started moving at the bottom where it appeared to be firmly held. And so what the folks at Asarco suspected was that there was a non-structural contribution to the geotechnical phenomenon being observed. Incidentally, the name for this area was Indian Springs. And so if you hear me referring to Indian Springs, think red blob on Highwall, and you'll have it about right. All right, so here is the technique that we went out and scanned the Highwall with, hyperspectral imaging, which is basically laboratory-based infrared spectrometry converted into the field. And so we take an infrared spectrometer, which is looking at light with a slightly longer wavelength than the visible range. So we take what the human eye can see starting at about 400 nanometers. My eyes, the longest wavelength I can see is about 700 nanometers, but with the infrared spectrometer, I can extend that out to about 2400 nanometers wavelength. And in that wavelength range, I can see what amounts to a lot more color. So my shirt looks red because it has a strong absorption at the wavelength that corresponds to blue light. And that would show up as this basically low reflectance of blue light at in any spectrum taken off of my shirt. Minerals have color in the visible range, but they also have absorption peaks that are kind of like color in that longer infrared range. And by looking at that up to 2400 nanometer wavelength, we can actually see that there's a bunch of peaks, for instance, this one, where we have color absorption, so to speak, going on. And we can use these spectra, the characteristic absorption patterns of different minerals, to figure out, okay, this spectrum matches this particular mineral. Now, we're used to doing that in the lab with lab-based spectroscopy, but in the field, what we do is we take our spectrometer and we scan over a large area, a high wall with a tripod or with a drone flying with a spectrometer mounted on it like so, and we collect a spectrum for each pixel in the image. That will give us one of these basically for every single pixel on here, and then we can take a set of reference spectra for representing different mineral types and classify our hyperspectral field data set against those. And basically, hey presto, we come up with a mineral map in which each pixel is colored according to its mineralogy. And so this is a technique that we thought would be good to apply at the Ray mine for reasons that will become fairly obvious as I get to the concluding part of the talk here. So the thing that made this possible, apart from hyperspectral imaging sensors, was drones, which are fairly cool to begin with, but they're extra cool for mining because they really bring a new way of flying to the mine. So hyperspectral imaging has been done for years, sometimes decades, from airplanes and from satellite platforms. And those are great if what you need to look at is absolutely flat and multiple tens of miles across. If you're trying to do detailed mineralogy on just a segment of Highwall, then satellite-based platforms don't have the resolution. And if you can fly an airplane really close to a Highwall consistently and get the imaging spectrometer pointed where it needs to go, then you clearly are missing your vocation because you really should be a stunt pilot. It's not easy to do, but drones allow us to do that and to put our spectrometers up close enough to the Highwall where they have the spatial resolution and the consistent height above ground that comes from terrain following mode to collect the data that we need. And so with drones, we're able to map the Highwall mineralogy, or for that matter, any other location, down to a resolution that is, depending on the flight height and a few other things, easily a centimeter. Well, could be anywhere between 1, 5, 10 centimeters, depending on how close we want to get. So in April of 2019, for about a week in April, we took a drone and an imaging spectrometer out there with Headwall Photonics flying it. It was a co-aligned hyperspectral imaging system with 170 SWIR and 270 V-near bands over a spectral range from 400 to 2400 nanometers and a spatial resolution of about 15 square centimeters per pixel. For those of you who are really, really nerdy or want to know about the exact equipment that we were using. Ground truth samples were collected during the scans, and we got some additional ground truth spectra from the mine where they had a previous Malvern Analytical run collecting a large number of spectra. The radar data were contributed by the Geotechnical Center, and then the hyperspectral data by Headwall Photonics, and we processed them and classified them here at the U of A. And then we also worked with Headwall, who did some magic with LiDAR to create a geolocated surface mineral map showing our results. And so this spectra up here are what we were using as a reference library based on the minerals that were known to occur at the mine. All right, I'm just going to let this video play here while I start talking about it. So this was a 3D mineral map of that Highwall area that we were looking at, color-coded by mineralogy. So it was made by merging our classified hyperspectral image, our mineral map, with the LiDAR point cloud that had been obtained flying a LiDAR disk on the same drone. And the colors represent different minerals, but particularly noticeable here is the stuff in that bright magenta shade. That was the color that we used for montmorillonite. And we'll talk more about montmorillonite in a second, but the main point right here is that there is quite a bit of it showing up on the Highwall. Mixtures of montmorillonite with other minerals are shown in red. So there's quite a bit going on here. Incidentally, the shrubby looking things here, those are little bushes. So not rock efflorescences or anything like that. So very cool visualization of some of the results. This was just one piece. We were out there for a week. We collected huge amounts of data all over the place, but I've always liked this one as being a very cool way to look at it. I did see there was a hand raised. Are we waiting for the Q&A, or is that something to handle now?
That's up to you, Isabel. We usually wait till the end. Looks like it
Okay.
went down, so.
Oh, okay. In that case, with apologies, we'll wait till the end and I'll be happy
Yeah,
to
no
take
worries.
questions then. Okay. All right, so the montmorillonite turned out to be a pretty common theme, and we found a large concentration of it right underneath the moving area that had shown up in the radar. There's an altered diabase up there on the high wall where, and diabase, chemically speaking, has exactly the perfect makeup to start forming montmorillonite under certain types of alteration. We also found a lot of other things like carbonate in the light blue in that image. Mostly that was in the early sedimentary units in the area. And then we found kaolinite and white micas in the quartzites and the porphyritic rocks, basically where we'd expect them. So the montmorillonite correlated well, although not perfectly, with the altered diabase. And because montmorillonite is a swelling clay, that we figure is a likely contributor to geotechnical issues, because if you look at the structure of montmorillonite, it is a type of smectite clay, so it's got this layered structure to it. And the individual layers can hold themselves together reasonably well. They're quite well bonded crystallographically. The problem happens in between those layers. Normally, they just lie on top of each other like a sandwich. But if you start introducing water, the water can get sucked into what we call the interlayer area. It'll trade out with trade places with whatever cations started out being there, and it will just start accumulating in the interlayer. And as it accumulates, it can cause the montmorillonite structure to expand just vertically by a factor of about 2.5 in one direction. The volume expansion from pure montmorillonite can be significantly more than 2.5. But either way, what this shows is that water is a problem. It's a problem in geotech to begin with, simply because it tends to reduce the amount of friction that's holding things in place. But in this case, we have the added extra ingredient of a swelling clay that once water hits it is going to start basically lifting any overlying rock and potentially start it sliding. And so our conclusion from that was that while there's plenty going on at this mine in the structural sense, montmorillonite is something to watch. It's not related to structures, it's related to an altered diabase, but it can also help contribute to geotechnical issues. But we learned a couple other things from this case study, which I'd like to cover briefly at the end. One of them is that we finally have a technique that can map clay distribution in the field. And that is important for a number of reasons that go beyond geotech. So to kind of talk about how geometallurgy works at the moment, most of the work gets done in the lab. So we do blasting, we have blast hole samples, we take them to the lab, we analyze them, we figure out what the mineralogy and the chemistry are, and then we have to interpolate into the wide space between the drill holes where most of the rock we're actually mining is. And so geometallurgy, my field, works by and large with pretty low information density compared to the volume we're actually trying to mine. And with this technique, it wasn't sensitive to every mineral out there. I mean, hyperspectral can only work with things that are active in its wavelength range, but it was able to detect some of the really problematic things like the clays, which are responsible for a disproportionate number of problems in mineral processing, in extractive metallurgy, and in other fields besides geotech. And so we figure what this provides is a potential opportunity to try and provide at least a modicum of continuous data, not just based on interpolation between spaced out blast holes, but actually showing the distribution of those types of problematic minerals over the whole mined face. And so closing off here with where we're planning to take this research next, hyperspectral in this case study and in others that we've been doing here at the U of A obviously has a lot of potential applications to geometallurgy. if you're out mapping the high wall, then that's great. But no matter how good a geologist you are, you're not going to be able to identify clay types or map their distribution just out in the field. And so this is one area where hyperspectral can help supplement existing mapping efforts potentially. But what I skipped over in this presentation while I was in the process of making all of this look easy was that the data sets that we get from a drone-based scan of a single area are very commonly tens of gigabytes. And computationally trying to extract the mineralogical information from that before we even start talking about the, coupling it with LiDAR and some of the other things that we can do to create those cool visualizations is a very labor and time intensive process. Most of the existing techniques for automating or speeding up data reduction and classification have been developed for other applications of imaging spectroscopy, like agriculture, urban planning, and land use, where you have a relatively small number of spectral types and they're very easy to tell apart. In a mine, you can have hundreds of marginally distinct mineral species that are going to look very similar spectrally, but behave very different in processing. And so the real need here is to adapt existing techniques for collecting, processing, and using hyperspectral data for the specific needs of mining. And so since I like to close with a little marketing pitch, sorry, I should have told you about that earlier, Julia. One of the plans for ongoing research in this is forming a consortium to develop some of those improvements that will enable hyperspectral to be routinely deployed in mining environments for this kind of work. And so this case study and others show that it's a very promising technique in an area where we really need the help. And the goal of continuing research on it is to get it the rest of the way there. I think that's all I have here. So I will be happy to take any questions. Thanks for listening. Hope we didn't lose too many people.
No, I don't think so. Thanks so much, Isabel. And anyone that has questions, you can use either the Q&A function or raise your hand. I think we can even let you talk to ask Isabel the question, or the chat, whatever you prefer. I don't see any yet. Very interesting presentation, I have to agree.
Thank you.
All right, well, we'll keep an eye out for questions. Oh, here we go.
Oh my.
They're flying in now. Okay, from Chloe, we have, how clean should the faces be to use the hyperspectral imaging?
Good question. Cleaner is better. This is a surface limited technique. And so what we're going to be detecting with hyperspectral imaging is what's on the surface. And so if your surface happens to be covered by a whole bunch of talus or spoil, then the talus and the spoil are what we're going to detect. If we have a bare high wall area, then we can see what's actually in the high wall.
Great, thanks. And then I'm going to let Priscilla has her hand up. I'm going to let her talk to ask her question. Priscilla, if you want to go ahead.
Sure. Thank you very much, Isabel. It was wonderful. So I have a question. I think many things are more sensitively detected if you can make repeat flights and have them be very registered. And I mean, in particular, things like trying to calibrate what the grain size is on a beach in a tailings pond by the rate of evaporation, the rate of drying after a storm. So you repeat measure. How is the registration of multiple flights and looking for a delta, something different from one flight to another?
Okay, so that's an excellent question. What's the repeatability or the reproducibility like? In the Ray study, we only flew each area once because of the amount of space we had to cover in a relatively limited time. Now, we did do ground truth sampling and tripod as well as drone scans, which allowed us to kind of double check our results, but the tripod data, because they're not linked to directly to the topography or the DEM, is not going to give you a direct check on things like the location and georegistration. We have a separate case study, which is not yet published, where we did actually do multiple flights at 3 different heights over the same area and checked both the registration and the actual mineralogy. And we found that while different heights give you different resolutions, and it does make a difference for objects that are, you know, very close to the pixel size, the location by and large was not off by more than, I think, a couple of centimeters. But this was with doing all of a fairly manual process of data reduction. And so what that would be if you just used like an automated batch processing algorithm to try and locate all of your flights. We have not tried that yet.
So
But
it seems like if this could be combined with, well, certainly with LiDAR, but also with some kind of thermal to look for changes, because different processes take place at different rates and they can be very distinctive. And I could see many experiments that should be tried that extend beyond looking at high walls, but very interesting. Thank you.
oh yeah, well, we're planning to try some of them and have already tried a few. So thanks.
Thanks, Priscilla. And then we've got one from Tom Aldrich. How many drone flights were done at Ray to collect this data? He's asking.
How many drone flights total? Gosh, I would have to go back and count, but I think over the time we were there, it was about a dozen. Not all in one area. We did experiment a little bit with some of the other areas.
All right, I'm trying to go through these in order, but by the way, if we don't get to your question, we'll be forwarding these on to Isabel at the end. So if we don't make it through them all, Isabel will hopefully be able to follow up with you afterwards. From Scott Silwick, this was actually my question as well. Was there any ground truth sampling to verify the total percent content of montmorillonite in the rock?
All right, so I'm going to split that into 2 questions. 1, yes, there was ground truth sampling. 2, did it help us verify the total montmorillonite content of the rock? Not as much as we were hoping. There were 2 reasons for that. 1 is that while in simple environments, you can use hyperspectral imaging as a quantitative technique, when you have the complexity of a drone's movement in there and something as complicated as the mining environment, we could technically get data that would give us a numerical value for the montmorillonite content of the rock. Would it be any good is the issue there. And I think at the moment we're staying away from trying to quantify things completely, because there are too many variables that can affect. The way we'd be doing it is by looking at the intensity of the reflectance spectrum, and there are too many non-mineralogical variables that can do that. It's also, montmorillonite, unfortunately, is also one of those things that would be very difficult to reconcile to ground truth data, because detecting it in something like an XRD analysis is actually quite difficult. A significant amount of it tends to show up as amorphous content, which is a category that can also include other minerals. And so at the moment, we've been working with this as a relatively qualitative technique, but something that can still show us where, the giant magenta blobs is pretty clearly higher montmorillonite content than a place that only has a few pixels worth of the stuff.
Okay, yeah, that makes sense. Thank you. From Seth Gehring, how are the data calibrated in the field, and will it work any time of day or night?
So at night, you would need to bring your own lights. It's a passive technique, and so you have to have a light source incoming to your rock. In the field, we calibrate using spectron panels, or in the case of the drone, a tarp of known reflectance. And so we know the reflectivity of that material. We fly over it when we get started, and that allows us to adjust the reflectivity that we're measuring on the rocks to that reflectance standard from the beginning and the end of the flight. Now, when a cloud comes over and puts a shadow on the area, then it does create issues because your incoming light changes. There are various techniques for dealing with that, like illumination compensation. But yes, that is something that you'd need to plan for and be able to work with in a mine.
All right. Thank you. And then I'm sifting through some of the other questions. Tony Hammond is wondering if the problem minerals, montmorillonite and other clays, are compounded. Do you see higher percentages of them around structures and faults in the area?
So did we see higher concentration of problematic minerals around faults in the area? Not really. We only did a very kind of quick look for that, so I'm not prepared to put my hand on the Bible and swear to that. But most of what we saw controlling the montmorillonite and the other problematic, clay and carbonate minerals was the rock unit and the type of alteration that they were in, not so much the structure. At Ray, a lot of the structure is way post-mineral. And so while it could, in some cases, did have hydrothermal alteration associated with it, most of the alteration minerals are going to be related to pre-faulting factors and be cut by structure.
And then we've got, how well did the drone data align with the existing highwall mapping and other existing data sets?
So with things like the DEM, quite well. That's partly a circular issue though, because you use the DEM to register the drone data too. We did some overlays showing the distribution, the hyperspectral results compared against the existing geological and alteration map, lined up pretty well. Could I give you a confusion matrix off the top of my head? No. But in general, we saw good alignment.
And then Sarah Martinez, she's wondering, would hyperspectral mapping of drill core samples from the site help classify the minerals of interest or help make the process quicker? Does that question make sense?
I think so. So hyperspectral mapping of drill core can do a lot, or any form of spectroscopy can help do a lot, because one of the things that's been emerging from our case studies is the need for a very good but site-specific reference library. There are any number of canned spectral libraries out there maintained by the USGS, the Jet Propulsion Lab, and others. And they're great for kind of first pass work. But if we're doing something at a fairly detailed scale in a mine, what we've been finding is we need to have scans of ground truth samples that are from that mine in order to get the best results when we classify the data. And so hyperspectral scanning of drill core can help provide that. And it certainly is quicker to work with the pre-existing database that the mine has than to try to go out there and scan a bunch of different representative rock and alteration types in order to build the library from scratch.
All right, I think that's all of them. Oh, sorry, I missed one. How close, I guess the question's about affordability. How close do you think you are to making it affordable?
It depends on the depth of one's wallet, really. So what is affordable for me and what is affordable for a large mining company would be two very different things. I think the equipment itself is pretty much on par with a lot of techniques that are routinely used in the mining industry. So things like lab-based spectrometers are cheaper, but for instance, QuemScan and large-scale powder XRD instrumentation, as well as a number of other techniques, are fairly pricey, but probably in some cases actually cost more than hyperspectral instrumentation. So it is not something that you would just go to Walmart and pick up on a whim, but it's also not the kind of thing that would be you know, out of the fairly ordinary for a lot of mining companies.
Perfect. All right. Thanks so much, Isabel.
Thank you.
We really appreciate you being here today. Wim is going to be sending out in the chat some links to our next chat or our next dig in talk. And I'll let Megan introduce the things that we've got upcoming. Go ahead, Megan.
Thanks. Just want to say a huge thank you, Isabel, for presenting today. It's a really interesting talk. As you can see, we're active on social media and ask you to follow us there for any up-to-date information from WIM. And I'd like to go ahead and make a note of our next month's dig-in, which is October 26th on the field acid rock drainage study at the Baghdad mine. And our Q3 event will be in person on Friday, October 1st. Registration's open and seats are limited, so please feel free to join and register for either of those. And I'll post in chat here. Oh, someone already did all that info. Thank you. Thanks for joining us today.